definition. So we want the definition of a labeled graph. Okay, so a labeled graph well, a labeled graph, yeah, it is a graph G together with a distinct label for each vertex of G. So we're defining label here as well. Okay, again, as are some of the definitions in graph theory, this one seems like a little self-referential, but all it is you're given a graph and then you name each vertex, right? Each vertex is given like a unique name. These labels are very often their colors or natural numbers, things like that, okay? So let me give an example of a labeled graph and you know why we talk about two different ones here. So let's look at this like path on 3 edges. And I can label the vertices as follows: 1, 2, 3, 4. Okay, so what? I mean, that's no different than anything we've done before. Sometimes we name our vertices V1, V2, V3, V4, and so on and so forth. Okay, so the label, though, if I give a different labeling to the same graph, it's considered a different labeled graph. Okay, so let's say I relabel it here with like 2, 1, 3, 4. Okay, these two are not the same labeled graph. They're the same graph, right? Like if you were to ignore the labels and ask, are they isomorphic? Are they the same? Yeah, I mean, they have the same set of edges among 4 vertices. But when you introduce labels, you're talking about a more complicated structure here. And these two are not equivalent because, for instance, if you think of this graph as representing like, you know, friendships on Facebook or something like that, absolutely person 1 and person 2 are not like indistinguishable. They're 2 different individuals. And in this picture here, 2 is friends with 1 and 3. And over here, 2 is only friends with 1. That's a different scenario, right? Even though the underlying, like, you know, network is the same, the underlying graph is the same. These are 2 different labeled graphs, okay? So different labeled graphs, okay? But just choosing labels doesn't automatically distinguish the graph, right? If you take a triangle here, if you think about this for a second here, no matter how you label it, this is going to be the same graph every single time because each vertex, you know, 1, 2, 3, is adjacent to all the other labels. So if I label it like this, 3, 1, 2, you'll notice there's the same adjacencies for each vertex, right? So one sort of way to check if 2 labeled graphs are isomorphic or not would be to like list all their neighborhoods for each vertex, and they should be identical across the 2 graphs. In this case, they're not. So vertex 2 and 2 is not same in both, right? That's why this is not the same graph here, okay? So the number of ways to label a graph to make it different is a challenging problem because it depends on the number, like, you know, this one here, there's maybe a few other labelings here, but like I could draw another labeling that's equivalent to the first one, but at first glance looks different, right? We could label it like 1, 2, 3, 4. And this one like looks different. Like if I'm thinking of these vertices in space and just choosing another labeling, well, where there was 1, there's 4, where there was 3, where there was 2, there's 3, and so on and so forth. But then if you look carefully at this one and compare it to this one, these are the same, right? The one has the same adjacencies here as it has here, and so on and so forth, okay? So determining whether 2 labeled graphs are identical or not is you kind of have to brute force is the only way for now to determine that they're the same. But anyway, so this is like a more complicated graph structure, okay? And what's important is the labels we're using, we're not repeating any labels. In the weighted graphs, when we weighted the edges, that was just a function that assigned values to the edges, and there might be repeats, and that's just something added onto the graph. This is a labeled graph is a structure, okay? So it's on a vertex set that has names. Okay, so what we want to actually talk about today is the number of different labeled trees on n vertices. That's what we're going to determine. The answer to this question is something called Cayley's formula. And let's just enumerate. Let's do some by hand here. This is a little tedious, but some of it's kind of nice. So when you have 2 vertices, I need to label trees. So I need to first of all figure out how many like underlying trees are there, and then figure out how many different ways to label it. Yeah, I see Eric puts up 1. There's only 1 tree on 2 vertices. Just this one too. And how many different ways are there to label this tree here? Also just 1. I can go 1, 2, or 2, 1, but 2, 1's the same as 1, 2 here, right, with the little examination. So that one's simple enough. When n equals 3, then there's still actually only one graph, because you have 2 edges, and they have to be incident. Otherwise, I mean, there's 3 vertices. There's no other ways to get trees here. But this one now, there's multiple ways to label it. What's the key feature of this one here? Like, what would determine my labeling in the first step? Does anybody see?
Your degree 2 vertex.
Yes, exactly. Once I've named my degree 2 vertex, then the other 2 vertices are sort of indistinguishable from that perspective, right? So this, I could label this with 1, and then this would be 2 and 3. But this is not the same as this one here, where I label this with 2, and then 1, 3, and then the last one here, 3, and then 1, 2. Swapping the bottom 2 vertices is not going to change. This is going to be the same labeled graph. But the central vertex, again, by following sort of this rule here, which I didn't state formally as the way to determine it. I mean, you just have to determine whether they're isomorphic or not through whatever means you have at your disposal. But in this case, clearly, right, the degree 1 vertex is different in all these, so they can't be the same graph. If it was like a cycle, think about a cycle for a minute. If you had a cycle, you can have like rotations and reflections and so on, and those are equivalent. Like there is some sort of geometric stuff hiding in the background, or algebra, maybe you'd say. All right, so let's do a bit of n equals 3. We'll see how much patience I have here. So with 3 vertices, we start to have a number of different underlying graphs, like unlabeled graphs. So again, this is a 2-step procedure for now. You can determine number of labeled graphs, number of unlabeled graphs, and then number of ways to label them. But I'm going to do a little bit different strategy here. Well, maybe it'll be the same strategy. The first one, let's figure out some labeled graphs here. So here's one, right? There's a star, you can have that, right? And there'll be a few ways to label that one. Yeah, Eric's saying there should be 4 of these, right? Because same deal, there's 4 different ways to give the center there, and then these are determined. So stars seem to be like sort of easy to enumerate. But then when you get things like, what do I have next here? Like some kind of path? I'm looking here. Yeah, well, of course. Let me draw the following path here. Okay. There's going to be a lot of ways to label this one now, because there's 2 vertices degree 2 and 2 vertices degree 1. And like if this is 1 and 2, then whether this is 3 and 4 or 4 and 3, like it's different there. Okay. So rather than trying to list them all out and figure out how they compare, I'm going to show a different strategy for enumerating them here. So what I'm going to think about, this is just a different way. So up here, we numbered them, and then we like thought about the architecture of the graph and figured, oh, these are different. Now I'm going to allow these to be labeled by the position the vertices are in space. Okay, so this vertex is at 0, 0. That's vertex 0, 0. This is 1, 0, 0, 1, and 1, 1. Right? That's their labels by their actual coordinates in space. So I'm always going to draw the 4 vertices in this fashion. And then I'm going to try and redraw this picture where now this vertex is not the center, but say this vertex is the center. Right? So this is a rotation, but again, if this vertex is labeled with its coordinate, this tree is different than this tree because now this is the central vertex. Okay, let's continue that strategy here. So now the center could be here. And then one more. I'm just trying to tell another way of doing this type of problem. You could go about doing the labels up here, keeping the same picture and just, go, this one here is easy enough to do. Okay. All right. So now this path here, this can be drawn in a bunch of different ways, but let's just work with this one and use the same rotational trick. So this path can be converted to this path, which is different than this one, right? Again, think of this as this vertex is adjacent to this one of degree 1, this one's adjacent to this one of degree 1, and now this one and this one are degree 2, so it's clearly different than this one. Okay. That one, and then the U. Okay, so those 4 are different there. But are we done? We're not done. There are lots more paths like these, right? Like what about the path that, let me change colors here and then I'll undo it here. What about the path that goes like this? Here, here, here. Is that listed here? That's clearly a different path than any of the ones on this list here. This kind of like this structure here. So we have to actually do those as well. So like this path, whoops. Oh, okay, well, whatever. That's yet another path. Not the one I drew in red, but yet another path here. Again, if you give these guys names, like if we say 1, 2, 3, 4, maybe that's worth doing for a moment. you can confirm that these are different without using the coordinate locations. Okay, so those stars are all different, right? The central vertex is 2, then 3, then 4, then 1. And to compare these two here, the ones above, like look at this. This says vertices of degree 3 and 2 are both of degree 2, but here 3 and 1 are of degree 2. So it's different, and 3, 1 never appears in this list here of degree 2. So this one's got to be different. And let's do rotations of that as well. So, okay, this is challenging for me, but I think it should be like this. The backwards n, and then the z, and then the n. Okay, and as I illustrated before, there's yet more here because there was this shape here, right? Again, if we label these, we can see that this has never occurred before. If we look in the lists above, we did have the instance where 3 and 2 were both degree 2, but when we had that, 3 was adjacent to 4 and 2 was adjacent to 1, like this guy here. But here it's different. 3 is adjacent to 1, 2 is adjacent to 4. It's still different than this one here, okay? And now we can rotate this one here. And finally, okay. And I think that's all of them there. How many did we get in this case? I mean, it's pretty easy. We got 16. So how do you know you're done? Yeah, it's not easy. I mean, once we have the formula, we'll know. But before we have the formula, like there's, I don't know, like a great way to do it. You have to keep listing them and check all the different ways of permuting elements. It's just a counting problem in disguise. But you can imagine when we get to like n equals 4, like notice that this one was split into 2 categories, right? There were the paths, and then you have to ask how many different ways can I label the paths? That's a counting problem. And there were the stars. How many different ways that to label the stars? But when we get to n over 4, let me just illustrate here. We're not in a big hurry here. If we were to do n over 4, well, what have we got? We got the stars, right? That's 5 vertices. Yeah, so we've got stars. We've got paths. Wait, what am I doing here? Everything's messed up. Yeah.
Before this case was also n.
Yeah, this is n equals 4. Yeah, sorry, n equals 4. N equals 3 up there. Yeah, thanks. So this is n equals 5 that I'm doing here. N equals 5. Yeah. So there's 5 vertices, 5 vertices, but there are other paths. Yeah, exactly. Right. I mean, there are other trees on 5 vertices as well, right? You can have like this picture here. I think that's it on n equals 5. Okay. And so now I have to figure out how to label all these. Well, the stars we know how to label. There's 5 of those, right? Choosing the central vertex can be chosen in 5 different ways. The remainder, the number of these is like, I'll leave that for you guys to figure out. It's not immediate. It's some kind of factorial with a division, maybe. Like there's a way to solve this. And then this one has its own, you know, what's the term in algebra? This is embarrassing. Symmetries, yes, right? Like that's what's going on here. It's the symmetries are what's important here, right? This has just all these symmetries by swapping these guys. The path obviously has some certain symmetries there. And this one has some weird symmetries as well. And so like, you have to figure out how many of these there are, which by the way, is not an easy problem to begin with. And then you have to figure out the number of ways to label each individual piece, which on its own is each individual problem. So what I'm trying to emphasize here is this is difficult. Like this is challenging to solve. In fact, what's this collection of objects here before we label them? What am I actually asking for in this first step? These would be number of what in this first step?
Spanning trees?
Yeah, or let's just say number of, I'm going to say unlabeled. That doesn't quite fit trees on n vertices. Right? So that would be our strategy for solving this. Yeah, exactly, Eric. So number of unlabeled trees, and then for each one, figure out how many different ways there are to label. And we've seen that it's not a consistent number of ways to label. It depends on the structure. So that's challenging enough. The real issue, though, in this is that this problem here, the number of unlabeled trees on n vertices, has no closed form formula. Like we don't have a simple description of these. Like there's a statement in the notes of like some bounds, and we do have like an estimate for it, but there's no closed form formula. So like we're not going to be able to solve this through that strategy, right? So no closed formula. No known closed form formula. So there's no like simple, like it's, you know, n choose 5 minus 12 times a trillion. There's no simple thing like that. And then even if you had that, you can't just multiply that by the number of ways to label, because the number of ways to label is different for each of these. So that's not going to be our strategy for solving this problem. We need some other strategy for figuring out the number of labeled trees. And so here's the answer. So this is Cayley's formula, or Cayley's theorem, if you like. So the number of labeled trees on n vertices is n raised to the n minus 2. That's it. It's a very simple formula, okay? A number of people, myself including, consider this maybe to be the most beautiful like theorem in all of combinatorics. Like this wildly complicated structure that, you know, the standard strategy would be incredibly hard to solve, comes out to this like really simple number, n times n minus 2, n raised to the n minus 2, okay? Let's just quickly confirm that it actually matches the things that we solved real quick here, okay? So 16, this is n equals 4 to the 4 minus 2, that worked, good. And then this one, n equals 3, is 3 to the 3 minus 2, which is that, so that's fine. And then this one, I guess this works too, 2 to the 0 equals 1, yeah. Okay, so at least it worked for those. So we had 1, 3, 16. It's kind of hard to see the pattern from those immediately. But yeah. So in this case here, if we were actually to try to do the n equals 5, we get 5 to the 3rd, right? That's 125. So really it would have been a rough exercise to actually go about doing those. I've never seen them all listed. Yeah, there's a lot of different labelings of these, and I think we got all the trees here, but yeah, okay. So in the next like 2 classes, we're going to give a number of proofs of this. I was hoping to do 2 today. I have my doubts we'll get through the second one, but we'll see. Maybe we can get it started at least. So this is the first proof. First proof. I don't remember who this is by, so it's not by Cayley. Okay, so what we're going to do to prove this is a common strategy, is we're going to count a more complicated object, okay? So count a more complicated object, and then we're going to divide out by the overcount, okay? And we're going to complicate this object in a couple of ways here. And in order to do that, I'm going to have a whole laundry list of definitions. They're all pretty easy, but just let me go through them carefully here, okay? So the first here is a rooted tree. So let's say rooted tree is a tree with a special vertex identified as the root, okay? So all it is like if you have a tree and you have a root, it means you just picked one vertex to be the root, and that's just a special rooted tree. So like, it's closely related to labelings. It's essentially a tree with one vertex being labeled. So here, like, I can call this, like, I'm going to do a capital R for the root. So that's the root of this tree. And I could draw the same tree over here, and I could say that's the root. These are 2 different rooted trees, right? It's the same tree and then the root. Now, the nice thing here is how many ways, given a single tree, can you root it? Especially if it's labeled, how many ways can you root it? And you just grab a vertex to be the root. You have the labeling and say vertex 7 is going to be the root. So take the same labeling, now vertex 9 is the root. Those are different rooted trees. So it's like it's a secondary label, right? I mean, there is no issue there, okay? A rooted forest, okay, so I'm actually defining 2 terms here because I don't think I've defined forest yet here, is a graph whose components are rooted trees, okay? So in general, what is a forest? A forest is a graph that may not be connected, whose components individually are trees, right? The metaphor works very nicely, right? So like, just a forest, here's an example, like this graph here, that's a forest. It has 2 components, it's not connected, and they're both trees. An individual tree itself is also considered a forest. It's a forest with one tree here. And then a rooted forest is simply a forest where each of the components is not only a tree, but they each have a root. So this is like R1 and this has R2, something like that. Okay, that's a rooted forest. So those are the individual pieces. Okay, so what we're actually going to count is rooted forests to solve this problem. A rooted tree is just a rooted forest where I have one component, okay? And then I have to somehow get rid of the root after this. But as Van pointed out, the number of like ways to root a labeled tree is just n. So we'll have to like divide out by some kind of n at the end. That's not really an issue. But let me add one more definition here. A branching forest, okay? Now, this is not standard. Rooted tree, rooted forest, all these terms, those come up all the time. Branching forest is only really used in this proof, and it doesn't add any new information to this definition. It just makes it a little easier to visualize, and it says the following. So branching forest is a rooted forest where every edge is oriented away, say. We can choose one or the other. So oriented away, whatever these terms mean, from the root in its component. Okay, so what does that mean? Well, I didn't add any new information. I just said, here's my rooted forest, and now I'm just going to add this extra like graphical help that each edge has an arrow on it that's pointed away from the root. Okay, so because it's a tree, this is well defined. So that's pointed that way, that's pointed that way, that's pointed that way, right? Each of these edges points away from the root. This one, root 2 is there, points out that way, then away, then away. Okay? Does that make sense? Like you just make the arrows, like everything flows away from the root. And you notice that the direction of these arrows is immediately just specified by the choice of the root. There's no choices. You have to go in one direction. So branching forest doesn't actually introduce any new information here. It just says, oh, also pretend your edges have this orientation. Okay? And this orientation of edges is something we'll talk about later in the class. This is something called directed graphs. We're just using it for now to help us out a little bit. We're not using any theory about them. These arrows will help us visualize what's going on here, okay? So we're actually gonna work with a branching forest, which all that is a rooted tree in disguise with like some additional stuff drawn on there just to help us keep our thoughts organized a little bit better. You'll see why when we get to the key step of the proof, okay? Okay, so, okay, Eric, did you have a question? You're muted here.
Yeah. Before we start, so
You bet.
rooted tree.
Yeah.
Is that like kind of assuming that all the things are already labeled? So like if you went to the graph where you have like the C,
Yeah.
the roots, so it's labeled?
Yes, yeah. For our purposes, it'll be labeled. All the trees we talk about now are labeled. If it's not, then like let me just illustrate because this is a good question. So like here, if I root, this is different than this, right? Say I don't have labels, right? These are two different rooted trees. But if it's unlabeled, you might say, well, these two are the same as each other for the same reason that labeling these guys down here was the same, right? These would be the same rooted unlabeled trees, but they're not the same rooted labeled trees because it'd be like, well, this is 2 and this is 1 here. And so they'd be different there in that case. Okay, yeah. So, but for today, every tree is labeled. As we saw, the unlabeled trees weren't particularly helpful in solving this problem. Okay, so let me just make one observation real quick. Is the number of labeled trees with root equals, we already mentioned this, n times the number of labeled trees. Both of these on n vertices, right? We just discussed this a moment ago. Adding the root gives you n choices if you're labeled, actually. So Eric's question is very well timed here, right? If your graph is labeled, there's n ways to choose the root. So if we count this thing, the number of labeled trees with a root, then we will get the answer back of the number of labeled trees just by dividing by n here, okay? But we actually talked about branching forests. So what's the connection here, okay? Yeah, okay. So what we're gonna do here is we're actually gonna count. So let's count. I have no idea why this please move this window away has popped up. Actually, maybe if I just resize my window real quick, it'll go away. I didn't do that. It's funny when I get like a pop-up there's a message in chat or something like that, it comes up and then that thing complains, but then it doesn't go away. All right, where's my mouse? Okay, so let's count number of n vertex branching forests with one component. Okay, this is all, and all these are is n vertex. Oh, okay, so let me just add labeled here. Because of course we're talking about, like I said, we're talking about labeled things here. Okay, so n vertex. It's, yeah. In some books, like when they prove this, branching forests are just assumed to be labeled. Since they're only being used in this proof, we might as well just not include that in the definition. But n vertex labeled branching trees. That's all that is, okay? So we're gonna count this in the following fashion. We're gonna build them up one by one, okay? By building them up one edge at a time, okay? So what I'm gonna do here is I'm gonna start with just the empty graph here. So graph with some vertices here and no edges. And what I'm gonna do is try and end up with an n vertex labeled branching tree. Remember, a branching tree also has a root. And I'm gonna do that by adding an edge at a time. And what I want to do is at each step, I'm going to have an n vertex labeled branching forest with like not one component, but more components. But each time I add an edge, I'm gonna destroy components. And so when I've added n-1 edges, I'll have a tree. That's the goal here, okay? So let's start with that many labels, vertices, and at each step, add an edge, okay? And so let me explain what's going on here. In this first step here, this picture is a branching tree, sorry, a branching forest, right? How many components are in this? Yeah, there's 6. Each of them has its own label. Like, again, we're gonna use the orientation here. So the label is the positions in the plane. And each of these is a branching forest. So what does that mean about this very uninteresting individual forest in each of these steps? Each of these also is the root of its own component, right? This component that has a root, and there's no choice but for that vertex to be the root, okay? So when I add an edge here, I'm gonna just take any old 2 components that I like and draw an edge between them, okay? And then I'm gonna orient this edge. In the first step, it doesn't matter. In later steps, it matters, okay? I'm gonna orient this edge this way, okay? So what that means is now here I have 1 less component because 2 got merged. These individual vertices, these are still branching forests, right? They have a root and all edges inside of this component. Let me change over to red. All the edges in this component, of which there are none, are oriented away from the root. Fine, not interesting. But this component is interesting. In this component, I now actually have an edge here. And what should be the root in this picture then? Yeah, the root in the lower left, this remains the root. This was the root of this component on its own, and this was the root of this component on its own, but now I oriented this edge, so this guy can't be the root anymore. So now I say that this piece here, oh, okay, that's the root. And if that's the root, then here I have a branching forest with 1 less component. I reduce the number of components. So let's say I continue this procedure till now I have k components, okay? We don't know what it looks like, but I'm gonna show you how to go from the kth step to the next step. Okay, so now suppose we have k component labeled branching forest. And let's build one with k-1 components by adding an edge. What the heck? Okay. Why does this happen? Now I can't. There we go. Oh, I got it for 1 second. Okay. Okay, so let's build one with k-1 components by adding an edge. So I want to count the number of ways I can add an edge. Let's go back to this example for 1 second here and figure it out here. When I drew this edge here, how many choices did I have for that edge? When I picked that edge, what's that?
N?
Well, okay, almost, Caleb. So I had n choices for like the left-hand side of the vertex. And then after that, how many choices did I have for the right-hand side of the vertex? N minus 1. Yeah, there shouldn't be a loop. So the number of choices in this first step was n times n minus 1. Okay. Now let's pretend that we have k components. Okay. So like here's my graph so far, and here's my k components. Maybe some components are still an individual vertex, but right, I've added edges to get to this point here. Each of these pieces is a branching tree. So each of these pieces has what I'm going to label in blue here. Each of them has a root in them, right? Now I want to add an edge that looks like this, that's oriented here. Where should that edge start and end? Or where should it end? So that edge is gonna, once it goes between two components, like here, that immediately becomes one component, okay? But think about the edges in this, let's do a different one. Let me draw two bigger components just so we can actually work here, okay? So say these are the two components here, and let's say the root's there and the root's there. Then the edges inside this component are all directed away from the root, right? That was the rule here. And same one here, away, 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 away. So if I add an edge to this graph and I go from like here to here, just let's do an example. What's going on in this resulting component? Are all the edges oriented away from the root? The correct answer here is probably like a shrug. Like, what's the root? Like, I had two roots and I added an edge. Like, who's the root? Well, there's no, if you think about this one for a minute, there's no candidate for the root. This one here, everything's oriented away. This one's oriented away. But then that edge is not oriented away from this root. And if I took this as the root, then this edge here is not oriented away from this root here. Okay? So this should suggest something here, a strategy. If I want to add an edge, where should that edge terminate in order to preserve the orientation rule?
One of the roots.
Yeah, exactly. So that edge, it can start anywhere in any of the components. It doesn't have to start in the root, but it better end up in a root, right? Because if I orient it this way, now this vertex here, everything from the blue one to this one was oriented away from the blue. And so it reached here and continued away from that blue and then went down to this one. And because everything was oriented away from this blue one, that continued the property of being oriented away from this one, okay? So we're adding an edge, but how does that edge look? Let me scroll down a little bit here. It's aggravating, I can't. Okay, yeah, I remember that's like the quick fix. So any added edge must terminate in a root of some component, okay? That's in order to preserve this branching business, okay? So that was the reason for introducing this branching rule, because if we didn't say the branching rule, you'd have to say, well, you add an edge, it has to go to a root, but like why? And if you see that you're preserving this orientation, it's clear that it's got to go that way. Okay, so it's got to terminate in a root. Where must it start? Can it start in a root? Like if this edge here, there's a way to erase, right? Yeah. Like if I get rid of this edge, and then say, what if it went from this vertex to this vertex, oriented that way? Does that still satisfy the rule of branching? Yeah, everything's oriented away from this vertex up here into there, still away. So I can pick it anywhere. I just can't pick it in this component, right? I can't have this vertex here go orient to there, because then I violate the tree property, right? So it terminates in the root of some component and starts in a different component, okay? So I want to count the number of ways to do this, but let's flip it around. Let's flip it around and do the following. In other words, starts anywhere, right? The starting vertex of the path can be anywhere, and terminates where? Where does it terminate? It starts in any vertex of any component, and therefore it must terminate in what? In a root, but not the root of the component it started with. So any of the k-1 other roots. Okay, so if we count it in this way, it's immediately clear what the two numbers are. Here, I don't know how to count it this way because I have k choices for the roots, but then how many other vertices can I choose for the start? Well, it depends on the size of the component that I started with. But if I choose the starting point first, there's n ways, and terminates in a root of a different component, then there's k-1 choices for this, because there's k total roots, and I have one root out of the running, right? If I say I'm going to start my edge with this vertex here, that root can't be the end of it, but any of the other k-1 roots can be it. So that means number of choices for this new edge is n times k-1. In the n time in this step, in the k, when I have k components go to k-1 components, I had this many choices. Any vertex can be joined to any one of the existing roots. Let's just scroll up real quick and confirm that that matched the number of choices here. Yeah, in this step it was fine. We had n choices for the first vertex and n-1 roots other than the vertex itself, right? There were all these other vertices were roots. So like now in this picture, let's just do the second step. Let me change over to green here. So if we continue this picture, in the second step, I could choose any vertex I wanted. Say I choose this vertex here, and then I have to choose any vertex that's not the root of that component, right? So this is a root, this is a root, this is a root, this is a root, that's not a root, right? That's no longer a root because that one, so maybe I orient it here. So here I had n-2 choices for that one there because this vertex was out because it was not the root of a different component. And then I can continue this. The next step I'd have n times n-3 choices. Choose any vertex, say I choose this one, and then I orient it to, so now this is the root here. I orient it to a root, let's say I orient it over here to this one. And so now this is a root. And I had n-3 choices because 1, 2, 3 vertices in that component were not available, and so on and so forth. Okay, so in total, and now we're almost done with this proof here. Oh, I'm undoing, okay. All right. So in total, the number of steps that we have is a product here. So in the, first step, and we go up to, how many steps do we take in this procedure? n-1, right? We're adding edges, sorry. That's each step is adding an edge. We'll add n-1 edges because the tree has n-1 edges. In each step, we have n times n-I. You can think of this as being indexed in the reverse, maybe is easier to say, right? The first step, we have n times n-1, then n times n-2, then n times n-3, then n times n-4, and so on and so forth, okay? In the very last step, you're only gonna have one choice because you're gonna have two components. You can grab any vertex, and then you're gonna join it to the root of the other component. So it'll be n times 1 at the very last step, which makes sense here, okay? But this can be simplified as n times n-1 times n-1 factorial, right? That's just what's on the left-hand side there, okay? So that's the number of ways to build up a branching forest edge by edge by edge. But this is not our answer. There's some kind of overcount here. So how many ways can we build a fixed branching, so labeled branching tree this way? So say, just as an example here, that we built up this branching forest that looked like this. Say this was the root, and so these edges are oriented this way. Okay, so say this was the branching forest, and I want to know how many different ways could I have achieved this by following the rule above. Does anybody see the number of ways that you could do this?
Yeah, well, so we've overcounted by n already for picking a root, but also, like, if we're adding these edges sequentially, that, like, you could, rearrange, like, the way that you add these edges in any fashion and get the same tree, but we don't distinguish that. So we've overcounted by n factorial in that regard.
Yes, okay, so So one thing we have to take away is we didn't overcount by n. We overcounted the labeled trees by n, but we're not counting labeled trees yet. We're just counting labeled branching forests or branching trees. So the root is there. But if I want to count this guy here, I've counted it in n minus 1 factorial ways, once for each ordering of the edges of, say, t, right? Because this one here, imagine I follow the procedure. Remember, at each step, I'm choosing to add an edge. The edges of this tree here could be added starting from the empty graph in any order that I please, right? If you follow the branching rule, if I'm going to build this one up under the procedure, I could start by adding this edge, and then adding this edge, and then adding this edge, then this edge, then this edge. Or I could have done it in a different order where this was the first edge added, then this one, then this one, then this one, then this one. There's a bunch of different ways to do that. There's as many ways to do it as you can put these edges in an order. There's n minus 1 factorial ways to arrange in order n minus 1 things, okay? So each of these branching labeled forests was counted n minus 1 factorial ways. So that's my overcount, okay? So number of labeled branching forests, trees, man. Is n to the n minus 1 factorial divided by n minus 1 factorial, which is n to the n minus 1. And now what Van additionally said comes into play here. The number of labeled branching trees is this, and how does that relate to the answer that I actually want? Well, this is equal to just the number of labeled rooted trees. Remember, being branching and being rooted were the same thing. When you give a root, you give the branches, you give the directions. It doesn't include additional information. So number of branching labeled trees over n, so the number of ways to cancel out the root, equals the number of labeled trees, okay? So it's just n times n minus 1 divided by n. I said n to the n minus 1 times 1 over n. That's not, there's no dot there. Equals n to the n minus 2. That's how you get rid of the roots, which is our answer. That's the end of the proof, okay? So this was like a procedural way. Actually, this strategy would actually work for building up these trees. The problem is doing this procedure would not be wonderful because n to the n minus 1 times n minus 1 factorial is a huge amount of steps. And then you have to do this cleanup by dividing out by the duplicates at the end. Because like we didn't describe a strategy for doing this labeling, doing this ordering of the edges in order to get a different tree. Jeez, I'm struggling today. Like what? Like in this step here, I didn't outline a strategy for like getting a different tree out of it at each step. I just showed there's the total number of ways in order to do this, right? Every single different way is produced here. And this many of them produce the same tree. So you have to divide out by that. And so you get the number of branching forests is just this, branching trees, excuse me, and divide by n to get rid of the root, gives you this here as the number of labeled trees at the end there, okay? I know this is a tough one, but this is a very nice proof of this theorem. Any questions about this? I'm obviously not going to be able to do the second proof today, but that's fine. So.